Hello and welcome to today's discussion on the future of nuclear energy, titled "Should Nuclear Power the Future?" We're going to talk about how innovation, collaboration, and education are shaping next generation of nuclear technology. I'm Caleb Brooks, professor in the Nuclear Plasma and Radiological Engineering Department in the Grainger College of Engineering at the University of Illinois. And I'm also the director of the Illinois Microreactor R&D Center, where we study small nuclear reactor systems and the ways in which they can expand safe, peaceful uses of nuclear power. We're joined by some colleagues from a reactor technology developer, as well as my colleague from MPRE, Rizwan Udin. Let's start with a round of introductions. So first, Rizwan, would you like to introduce yourself?
Yeah, so I'm Rizwan Uddin. I'm a faculty member and department head of the Department of Nuclear Plasma and Radiological Engineering at the University of Illinois. And I've been here almost 30 years now, and I am also an alum.
Thank you. Glad you're here. Florent and James, would you like to introduce yourselves?
Absolutely. So, yeah, thank you very much for having me on. I'm James Walker. I'm the CEO of NANO Nuclear Energy. My background was as a nuclear engineer and a physicist. Got my start on submarine reactor systems, and then I worked on reactor core manufacturing, nuclear fuel reclamation, and then obviously most recently building out this company with Florent. I'm happy to talk a bit more about the company as well after Florent introduce himself.
Yeah, thanks, James. Thanks, Caleb. So I'm Friday. I'm the CTO and the head of reactor development at NANO. I've been there for a little bit over 7 months. I started my career working for the national lab, so designing advanced reactor, and joined the industry a few years ago. Now with NANO, pushing forward some advanced reactor technologies.
Fantastic. Yeah, would you like to talk a little bit about nano nuclear?
I am. So I'm also happy to put it into a context at the moment of what's happening in the country and the world with regard to nuclear, because you might have heard terms being thrown around like nuclear renaissance and things like that. And what that's referring to at the moment is this enthusiasm that's national, but also international for advanced reactor systems to come in and service things like data centers, AI, but to co-locate with remote locations, providing power in areas where nuclear has never really been deployed before. And what that's involved is smaller systems. Everyone's probably familiar with the kind of Homer Simpson nuclear power plant, the big civil nuclear power plant. We're looking at much smaller systems. So our company, likewise, when we started off, we were concentrating on very small systems. And the reason why we were doing that is that we saw a potential in the market for making sort of 1 megawatt electric systems that were going to go into places like mining projects, oil and gas, military bases, island communities, places where nuclear hadn't gone before, but also nothing else can go, such as gas, solar, geothermal, hydro. These are very locationally dependent energy sources, but nuclear can be put anywhere potentially to power these locations. But we began the company a number of years just before this sort of interest in the tech center came about. And how this came about was that the tech industry have these huge projected energy demands. And how that's happened is that they began examining how much their data centers would use in terms of power. They realized the grid would need to have billions of dollars, if not trillions of dollars, invested into it on a national scale to upgrade it to a point where it could outlay the power that they would require to power their data centers. And they realized that was just not feasible. They're not in the business of building back national infrastructure. So they began examining any other solution, which involved gas, hydro, solar, geothermal, whatever it was. But they settled on nuclear. And the reason why they settled on nuclear was because even if you've got enough coal or gas, you still need that infrastructure upgrade, or you need more pipelines, or you need transmission lines. It's very expensive. Solar, geothermal, wind, hydro, very intermittent technologies need big battery storage systems, but a lot of them are also very locationally dependent. So you lose that flexibility of being able to site. So the tech industry essentially got locked. They were very energy agnostic, but they got locked into nuclear. And when that happened and they began investing into nuclear, and you've seen investment coming into 3 Mile Island or AWS investing into X Energy, that sort of drove this sort of nuclear renaissance, and it really did pick up. And that it picked up around about the same time that the Department of Energy was investing billions of dollars into building back national infrastructure around the nuclear fuel cycle because there was the war with Russia, and we had been sourcing a lot of material from Russia. And the US wanted that national capability built back. And that just coincided completely with the tech industry's interest in nuclear at the same time. And when that happened, our company began looking to partner with larger reactor developers. And we spoke to a number of them. As we were doing that, and we were putting together partnerships, an opportunity came up to buy out a very advanced tech that had been very heavily invested into. And so we bought out that tech. And with that came big projects, opportunities to be involved in the nuclear renaissance, built to provide power for the tech industry. And so in recent months, we've been putting together projects to build the US's first microreactor, as well as the first microreactor in Canada at the same time. And those projects are both going ahead. So we've been a very pragmatic company. We've tried to take a very holistic approach to how we achieve things. And that's even began us down the road of looking at the fuel supply chain and investing into that to see how we can de-risk our fuel. So NANO's grown very quickly over the last few years. We went public in 2024. I think we were the best performing IPO in that year in the US. And that's given us the ability to raise the capital necessary to build these big infrastructure projects. And so Florent has been part of that. His recruitment has meant an upscaling of our engineering team. And so now we're proceeding as fast as we can towards constructing a fully operational reactor and getting it licensed. And then the intention will be, once that process is completed, to have a production line of reactors that we push out the factory door and we ship all over the world. Initially starting with North America, and then beyond that, we really have no limits on how many of these we could sell and the sort of market demand for them.
Yeah, terrific. And I think NANO Nuclear has a kind of a line of technologies, but in particular, there's a Kronos MMR. Florent, would you like to talk a little bit about the overview of the Kronos MMR?
Yeah, sure, Caleb. So, if you go on our website, you'll see there are multiple reactor technology listed there, and there was even more before, just because of what James explained on the history of the company, that took the opportunity of acquiring technology that were more advanced in their design process. So we currently are holding on to 3 design, but the one that's by far the most mature and advanced is Kronos. The other 2 are smaller implementation of it, so I'll talk briefly about them. They are catering to more niche markets. So this is, something NANO is also developing, but with a lower priority. So Kronos is a larger of the reactors we're proposing. It's still a micro reactor. So compared to the reactors that people may be used to see, around, especially in Illinois, they are significantly smaller. They would fit nicely into a small town or university or other communities. This is a so-called Generation 4 reactor technology. So it's a HTGR, that stands for high temperature gas reactor. And the big advantage of these technologies of the Gen 4 reactors, it's their safety is what we call passive safety. So it's a significantly enhanced passive response to any event, which makes the safety case and the implementation of the technology much more straightforward. For Kronos, on top of leveraging the physics, it's been designed around the idea of using ready-to-go technologies. So we're not looking at pushing the envelope on temperature, on pressure, on any new materials. The intent is really to provide a solution as early as possible to the energy needs all around us. I mean, all of us have surely seen in the news every day more power demand from the data center, from remote communities, from the industry. So our target is not to have the most necessarily innovative reactor, but to have a reactor that works, that is safe, and that we can deploy as soon as possible.
Fantastic. Yeah, so thank you to those who registered and all of your pre-submitted questions. We've got a lot of questions to potentially go through here. So we've talked about some driving forces, the tech side. Maybe we talk more broadly about how the perception of nuclear has evolved in the recent years, and maybe kind of what's behind this global momentum to increase the interest around nuclear that we've seen over the last 10 years or so.
It's a good point, because I think if you look at data at the moment, it's showing that public sentiment, so support for nuclear, is at the highest it's ever been. And maybe that's a generational thing. It's interesting to actually speculate on why it's so negatively perceived, because if you were to look at, say, deaths per gigawatt hour for nuclear energy, like it beats out everything. Like it would beat out wind and solar in terms of safety, in terms of, you know, the number of deaths that have resulted from nuclear, in terms of the power that's gone out. But I think the fact that it began with a weapon has probably created this sort of negative connotation that's had a psychological effect that has stayed. But the new generation hasn't really grown up in the Cold War, and they've not had sort of nuclear Armageddon hanging over them. And so the perspective can be a bit more objective around nuclear energy, and appreciate that the energy side is a completely separate thing to the military side of things. And then that's probably why it's got bipartisan support now on both sides of the aisle, and why the young generation is very pro. I mean, there has been obviously a big push to go more carbon neutral. Obviously, nuclear is a big supporter of that. But like the main thing is that there's been a drive as well, coming from not just the US, but every country, like I think it was COP 28, the last one. There was a mandate there to increase the world's nuclear energy output by, was it 3 times by 2050? So that's going to need a huge amount of construction and project. And it's trying to tackle all sorts of challenges. So climate change is one of them, but also it's about energy sovereignty. And we've seen how countries like Germany, they try to move away from nuclear power. And what happened when they moved away from nuclear power is that they became very dependent on Polish coal, and they became, ironically, very dependent on French nuclear. So their carbon footprint went up, and their cost of energy went up. And that seems to be a consequence that people are observing and saying, we can't really move away from nuclear without significant consequences. And now even Germany, as a result of that decision, has a huge reliance on Russian gas, as an example. So their foreign policy is actually very limited by their dependence on what could arguably be a hostile power. So
Yeah, I would, just so, at a high level, there is a lot of study that shows the index of quality of living around the world is directly proportional to the source of energy available and availability to energy. And even now so more than ever, with we see the revolution around AI and data center, we use more and more power. A lot more countries are growing up, not just in the US. The only source of energy that is currently highly scalable is nuclear. Because with 1 ton of fuel, you can fuel one of a reactor, for instance, for several years, for 4 or 5 years. And 1 ton of fuel, I don't know if you see on the camera, but this is kind of a big pot. It's a few gallons in volume because of the density of the fuel. So even we say 1 ton of fuel, it's not a huge volume. So it's very energy dense, so very easy to deploy. We don't have to have natural gas or any supply of product. We don't have any intermittence. So I think there's a recognition and better understanding of the technology. There has been, 60 years of history, 60 years of R&D, of learning, a lot of investment from the government, from the US government. This country has been pioneering a lot of the understanding of that technology. The universities like UIUC, but other universities across the US are recognized as, world-leading institution in that space. So I think it's the mix of need, of education, of better understanding that makes it a lot more attractive now. Now, it comes with, this is not the first nuclear, revolution or, that happened a few years ago. There was the same a decade ago, a bit over, there was already a push for it. And it's really now depending on how we execute it. The key difference between before and now is the type of technologies we have are not the same as the one we've built 60 or 40 years ago. So I think there's so this concept of, rather than having one solution and making the need fit the solution we have, is there are the needs, and we are able to bring to those needs a tailored solution to really, meet the exact conditions that are required.
Yeah, I agree. I've seen that on the international stage. It seems like the ability to expand economies, move into just more productive economies, comes down to clean, reliable energy. And then nationally, the bipartisan nature. It's so surprising to see anything bipartisan these days, but nuclear tends to be that. There was a time I remember where you had to give up your political affiliation to support nuclear, and that is no longer the case. And so I think that's really helped on the national side. I'm curious now, from a university standpoint, Rizwan, as a department head, how are you seeing the interest in nuclear from students?
So thanks, Gail. As you well know, I mean, the interest in nuclear has been always sort of cyclical. There are some branches of, education that see that cyclical nature of student interest, and it goes up and down. And we have seen our own. But so the last big push was before 2011, before Fukushima. The numbers were going up significantly. There was Renaissance 1.0, and then there was a slowdown. Around 2012, 2015 timeframe, the numbers started to go down. But then, once again, as we said, James mentioned, it's a generational thing maybe. The big push has started to come with the sustainability concern and the global warming and those concerns. And the fact that we wanted to get away from fossil fuel and CO2 emitting technologies. And companies after companies after companies, especially high-tech companies, as well as universities, started committing to being carbon neutral by 2030, 2035, which seems nearly impossible at this point, unless this new technology really comes on board very quickly. And the same thing then started to reflect on the number of students who were interested in studying nuclear engineering. And so the numbers started to slowly, increase. But then the big pushes started coming with the AI boom and the big, huge demand that, again, James and Flora, they mentioned that the demand is now so huge that a lot of people are realizing that nuclear is maybe the only answer, because the other sources of carbon-free energy are so intermittent that unless you have a major, major breakthrough in energy storage technology, and that comes down to, really, really becomes cheap, our energy need can only be addressed by nuclear. As a result, if you look at the number of students, for example, in our own department, I'll give you a little bit of a history of the department going back, started back in the early 60s, like many other nuclear engineering departments. So we develop the workforce and we do the fundamental research and some applied research. But the primary goal of universities is to train the workforce for the field. And it was initially a graduate-only program. And then in the mid-70s, 74 or 75, then the graduate degree was introduced. And the department has been usually, a small department, relatively speaking, compared to some of the other larger engineering departments in the college. But the last incoming class, all of a sudden, there's huge interest, and we have the biggest class ever as coming in as freshmen. And these students are really eager to work on these Gen 4 reactors and go and address the energy problem, and find solutions to the energy problem using nuclear. Of course, there are other aspects of the department. There's of course the fusion side as well as the fission side. There's plasma technology that we also cover in the department, and the radiological science, where the uses of radiation are used. Radiation is used either for therapeutic purposes, medical imaging, and of course, then we need to have health physics and radiation detection for national security. All those aspects are also covered. But as far as the power part is concerned, that is usually the biggest aspect of the department, and there is significant interest. We are thinking about how to ramp up our classes, how to ramp up our teaching labs, and students are very excited. So hopefully this will be much longer term, and as long as we have companies and industry that is coming up with the solutions to the problems and need the workforce to be developed by us, I think we are in this in the long haul.
Yeah, I'll comment quickly on that. If you can graduate your student very quickly, then we can definitely manage them. Not just us. I mean, there's a huge demand for qualified and well-formed nuclear engineers. So right now it's definitely a good time to see the growth in your department, and we definitely benefit from it on the back end.
It's a good time for high schoolers to be considering nuclear. I've seen what Florent is paying some of the graduates that are coming out of university, and they're more than what I got paid after 10 years as a nuclear engineer. So like there's a squeeze on them, so they can, you can profit off it.
Yeah, many companies steal away our master's students before they go on a PhD. So just let them get their PhD.
You're very welcome, Caleb.
And then just let us get our PhD students out. Yeah. Fantastic. So, in the pre-submitted questions, a lot of questions around public perception. Some in a cautionary way. How are you going to get people to accept nuclear? Some in a maybe more positive way of like, is this technology now able to come to us? Is it now able to go to a city? Is it now able to go to an end-use application? So we saw a lot of input around those two lines of public perception, and Fukushima was mentioned. 3 Mile Island is another one that's pointed to for public perception consideration. So what is different by going small in your technology? What is different? What about your technology kind of mitigates that or has something new to say to the public perception discussion in nuclear?
I'm sure Florent will add on to my comments about the fuel, but it's interesting too, because you mentioned Fukushima and 3 Mile Island, but these are incidents that a lot of people aren't aware that no one died in either of those incidences. They were I think the 3 Mile Island was the biggest nuclear disaster in US history. And Fukushima obviously just killed the nuclear industry in Japan, but in both circumstances, nobody died. And I think that sort of highlights the difference between the public perception of nuclear and the reality of nuclear. So that needs to be contended with. But what is nice about the messaging now is that in both those incidences, there was core melt, and that can occur through a number of reasons: loss of coolant, loss of pressurized system, boiling water, whatever. But the fuel that is now going into the modern reactor systems, particularly with TRISO fuel, which is what I believe the vast majority of advanced reactor companies are utilizing, it can't melt in the same way. So, for instance, in the past, you would have to build a big light water reactor system. You'd put sort of a 10-mile radius around it and say that's its exclusionary zone, and nothing's allowed within that parameter. Now, that has been removed because the big risk with nuclear, that meltdown, has been removed from the equation. So you can put it in the middle of a college campus or in the middle of a city, and you can't get the same disaster event. That's very good messaging to do. The things that people are scared about, radiation release, contamination, maybe even people being killed, it's just not feasible with the new tech. I think that's an important thing.
Actually, it's for me, it's a question that's very close to my heart because it's a very complicated question. So I mean, the answer is what James said, but how to convey it is also the challenge. So why what James said is accurate is because now those new systems, those new smaller reactors, they all rely on the physics, which the physics is an accepted fact. Just like gravity is one of the key physics parameters that goes into play, that does guarantee the outcome of an accident, and this is not relying on any active system. So in the current fleet of reactors we have what we call ESF, engineered safety system. So they are the system that need to keep functioning in case of an accident or incident. A lot of those are currently what we call active systems. So they are actuator. There is an action that needs to be taken. With those new smaller reactors, the Gen 4 reactors, we were able, in our case, to design it with 0 ESFs, so 0 active systems. So, sorry, I misspoke, not 0 ESF, but none of them are active. So we don't need to take an action. It's just reliance on gravity, reliance on heat conduction, etc., that is now well understood. The challenge with that, to communicating with the public, it requires having this minimum understanding of how the system works. So this is a joint duty between the university, between the technologies like us, to convey that. So we need to find a way to convey those phenomena relatively simply to the public. And sometimes we use the analogy of just dropping a ping pong ball or something like that to kind of translate that to something that speaks to everybody. But understanding that now, because we have a better understanding of those technologies, we design them in a way that no matter what happens, there's no need for an action to keep it safe. The consequence of that is, historically, when you build those big power plants, again, we have many of them in Illinois, we have what you call an emergency planning zone, which was 10 miles radius around any facility. We are able to demonstrate and guarantee, in our case, that our EPZ is 0. So it's located to the facility, to the building itself where the nuclear reactor is, which means we can put that in a city, in a town, we can put that next to an industrial facility. There's no need for really having this big zone where there's a lot of preparedness action that needs to be taken. And that should really help with also, the public acceptance of it.
Yeah, with nuclear, what is unique to other power generation sources is that when you want the reactor to shut off, when you want it to stop generating power, it doesn't go completely to 0, right? With coal, with natural gas, if you want the power to stop, simply stop supplying fuel or stop supplying oxygen, and the power goes to 0. With nuclear, physically, it's not going to go to 0. It's going to initially go to about 7% of its operating power. And that's why for large nuclear power systems, we need to have these active, always cooling to deal with that, what we call decay heat, that 7% or so that decays away with time. As you go smaller, that 7% remains, but it becomes much more manageable. You're not 3,000, not 7% of 3,000 megawatts, 7% of maybe 50 megawatts. But then the other angle that I think is important that was alluded to is around fuel. So what is new about fuel and how does that factor into the safety equation?
So it speaks to what Florent has been talking about with the physics of it. So a lot of the advanced reactors utilize a higher level of enrichment within the fuel. I would say the majority of actually advanced reactor companies at the moment are looking at HALEU fuel, which is really anything between about sort of 10% to 20% fuel enrichment, and the enrichment isotope being uranium-235. And that's for a number of different reasons, fuel density, refueling purposes, that kind of thing. So there has been an examination that the capabilities within the country need to be built sufficiently to be able to mass manufacture that particular type of fuel. I think we've taken a very proactive approach so that we know that there's probably going to be a bit of an extended timeline on the HALEU fuel compared to when we could get LEU plus, sort of up to 9.9%. So our reactor will utilize LEU plus initially, but we have the option of directly switching over without any significant design changes to the reactor system. So the fuel has been an important factor in this. We've already touched upon the form it's going to take in the form of TRISO pellets. Essentially, if you can imagine a more enriched uranium-235 amount of uranium, but very, very small and pelletized. So essentially, it has its own containment system into it. So if you can sort of imagine you were to hit the reactor with a missile or something like that, just as a complete hypothetical, just to try and demonstrate the inherent safety of the system. Initially, you're going to blow up that reactor system with a missile, and the fuel will be separated. So actually, it will become less critical almost immediately because the critical mass will be separated. But the individual fuel pellets will also be contained individually too. So you have a dispersion event essentially, but it's already containerized, and the safety of the inherent system is built into the fuel design itself. That's a very extreme example. On a less extreme example, if there's fundamental breakages within the reactor system, that fuel is still containerized. It's not going to melt down. You're not going to get those accident scenarios that you got at Fukushima or 3 Mile Island. And when you do have that ability to contain your fuel like that through a TRISO form, you can go for those higher levels of enrichment. And if you are shrinking the reactor down, it's in your interest to put higher levels of enriched fuel into that system. So it's a very interesting change that's been made possible. And the TRISO is not a new thing. The DOE invested billions of dollars into qualifying TRISO fuel to enable advanced reactor companies like us to be able to utilize it.
So I think we haven't defined what TRISO is. So let me maybe go over that for the sake of everybody who's not familiar with it. So TRISO fuel can take, there's a kernel, which is the fuel itself. In our case, it's UCO. It could be UO2, could be uranium nitride. But the key of the TRISO is there are multiple layers, coating of silicon carbide. Silicon carbide, if you're not familiar with it, this is one of the hardest materials on Earth. So this is what we're relying on to really retain, all the fission products, all the elements are within the nuclear fuel. So even if one layer breaks, even if 2 layers breaks, there's still another layer that protects it. And the size of this TRISO, we're talking 0.5 millimeter of diameter. So like imagine a bunch of big, sand grains. This is what the level of technology we are able to achieve. This country is producing this material. The United States is producing the TRISO. We have this technology where we can map these tiny, tiny elements, and each of them is self-contained. So that even if one was to break to go through the multiple layers of the TRISO, it's only the material from that tiny, tiny amount that will be released. All the other ones are very unlikely to fail or crack at the same time. So that's really what's shifting, the conundrum. Now to James' point, the melting point of these are ceramic material. They are several thousand of Celsius and above. So before reaching this temperature, almost everything else will be melted, and the TRISO will be the last to melt.
And by operating at lower temperature, you can easily mitigate that decay heat through conduction, natural forces to surrounding structures to prevent it from getting to those high temperatures.
Yep, thanks to the physics.
Yeah, thanks to physics. That's what we like. That's what we like. So what are the barriers then? What's preventing, or what are the challenges to rapidly deploying small nuclear reactor systems?
There's probably a few. I know that the federal regulator, the NRC, has taken a bit of criticism for very long licensing periods, but like I wouldn't say they're the fundamental block. They're there to support you through the process of assessing the safety of the reactor system. It's odd because the nuclear energy in the US is, say, 10 times more expensive than China, and a lot of the reason for that gets sort of put onto the NRC as being responsible for that. They are trying to reform themselves in ways to facilitate these advanced reactor systems going out. So they are trying to do their best to help here. Just to give one example, I think it's Part 52, Subpart F is a regulatory mechanism to allow for, as soon as you've got a licensed first-of-a-kind reactor, all the subsequent reactors produced after that can deploy without further regulatory engagement, provided the deployment site meets certain environmental considerations, seismic, flooding risk, things like that. So the NRC is taking measures to reform itself to allow for this sort of big wave of nuclear to go out the door. I would say personnel is a bit of a bottleneck. You mentioned Fukushima earlier on. That did lead to a sort of a loss of people within the nuclear industry. So you've got kind of like the old guard and then the young guard, and then there's a gap between. Obviously, there's a big recruitment drive to bring people into it, but it takes a long time to train a nuclear engineer and even longer to get them experienced. So that's one challenge. I would say public perception might be a small one, but like as we mentioned, public sentiment has been very supportive in recent years, and it's only increasing. But they add together to create this environment where you're trying to do something for the first time, against a backdrop of some, demonstrating technologies that haven't been observed before. And of course, there are other challenges too for a reactor company. The capital investment necessary to take a reactor from paper reactor, which I think me and Florent could probably design in our bedrooms, but like to take it from that to a fully licensed constructed reactor ready to go out to market, you're looking at raising an enormous amount of capital. So you have to be aligned with people who are able to raise you the necessary financing. Like for instance, we're very lucky in our company. A lot of our senior personnel have banking backgrounds. That's been very useful to facilitate us with the capital we need to actually build this out. That could be one of the biggest bottlenecks. And I'd say the biggest bottleneck after that might be, what is the most viable type of advanced technology? I think we've seen a convergence towards what we're doing, high temperature gas reactors that utilize TRISO, but there's other innovative technologies like heat pipe technology, fast reactor systems. And it's going to be an issue of which is the most commercially viable and most economically successful type of reactor. So that still needs to bear out. So.
Yeah, I mean, exactly what James said. I will, slightly formulate in the following way. For successfully deploying a nuclear reactor, you need, several things to come together. And James, mentioned most of them: money, customer, technology, knowledge, team. And it's rare to get all of that coming together, and that's a highly politicized realm. This is what we opened the discussion with. There's a shift of the demand of energy. It used to be utilities only. Now we're looking about, small grid, microgrid, beyond the meter deployment. So, for me, I think most of the nuclear technologies have a place. They need to find their customer. Not all technologies respond to everybody's needs. Now, in terms of execution, there is the alignment on all those things. And for us, NANO luckily has been well funded recently. So, the money has often been an issue because this is not deploying a nuclear reactor is not a 6 months effort and you're done. This is a technology that's pretty serious, that is well understood now, but this is one that's heavily regulated for right reasons. And because of that, you are not cutting corners. There is no fast track. You need to do your work. You need to get everything coming together. This is not just designing an engine. This is designing an engine. This is a full car with a road that goes with it. You need to integrate that with, the electricity distribution system. So all of that makes those not necessarily mega project now because our projects are relatively small in size and overall investment, but there's a lot of core, areas of competencies that need to come together. So I think for us, one of the main daily challenge is integration and coordination of all those experts together. So this is really what's going to make or break deployment of these technologies. Everything else currently is well aligned in this country to see some great success in the coming years.
May I add, what about supply chain, like the pressure vessel? I mean, do we have the technology? Are we dependent? How are you going to address that?
Yeah, it's a very good question. So pressure vessel, for us, I mean, the short answer is because we're going small, that we have a lot more options to get that from. When we are looking at a pressure vessel for large light water reactors, we're talking about mastodon that very, very few forge or factory can make. And, you can probably count the number of qualified vendors on your end. So not just a few across the world. So, and it takes a lot of time. And you can also understand that if there is a mishap with the production of it, you need to probably scrap most of it and redo it. Now, with smaller vessels, like we need, we're talking 4 meters in diameter, give or take. The length is several meters. There are a lot more shops in the US, in North America, we can make those. They are a lot more easily transportable. That being said, they still need to receive a nuclear certification. So this is a big part of it. This is why we are carefully selecting our providers, especially early on, to make sure we can proceed. We already hope and we forecast that in the next few years, we'll see a lot more qualified providers going to get those certifications to be contemplated as potential providers for us or for equipment for reactors.
It's quite an optimization. You have the end users and what they need. You have a regulatory framework, which you want to be extremely robust. I mean, that goes back to public perception. We want the nuclear industry to be heavily and appropriately regulated towards safety and ensuring to the public that technologies that are given the green light are safe. But by going smaller, you alleviate a lot of the challenges around. You make it easier for the regulator to put that stamp and say this is safe because of the the benefits of lower decay heat, because of the benefits to your fuel. But it's quite an optimization problem to try to work. And so yeah.
So maybe what about the issue that we used to back when I started in the nuclear business? It was always the economy of scale. And that's the reason why we started with 100 megawatt, then 300 megawatt, 600, 900, 1,000 megawatt. And the argument was economy of scale. So now that thing has been turned upside down. So how confident are you that this model, the micro and the small modular reactors, will work out as far as the cost is concerned?
So you raise a good point. Economies of scale is actually very important, like to consider like the commercial success of the reactor systems.
Yeah.
And generally, the bigger you make a reactor, the more economic that reactor will be compared to smaller reactor system because you get more power out in that way. The advantage with the smaller systems is that this was almost like an industry solution to the challenges of big nuclear. Because if you can modularize the system as much as you can then have a production line where you can achieve economies of scale just through the mass manufacture of the components, which leads to the mass manufacture of reactors, and you achieve economies of scale that way. So it's still inherent within the problem, but you're just transferring the challenge to the production of the reactor systems. And if all those subsequent reactors don't require licensing too, then Actually, I think our studies show that you somewhere between about 500 megawatts and a gigawatt, you start outcompeting the economics of a large light water reactor system. But with our system, I think we've made a reactor as large as you can possibly make it and keep everything modular. So everything we've got, we can move by road. If we were to make it any larger than this, then things like the reactor vessel, which Florent just spoke about, you would just exceed road weight limits and so you would then have on-site fabrication, as Florent touched on, very expert process that could go wrong. And if you get it a little bit wrong, you have to scrap the whole thing. But if you have expert fabricators that have got nuclear certified on these vessels, and they can just roll these things out, doesn't matter where they are, and you can move them by road, then you're not limited anymore by the number of sites you have. You can just stockpile these things if necessary, and then roll them out the door. But even on individual sites, you're going to have an economic benefit of deploying more of those reactors to one site, because in our case, whether you do 1 or 10, a lot of the infrastructure will be the same. So like the adjacent plant that converts all the thermal over to electric, that could do 1 plant. It could do 10 reactors. Could probably do more than that, I would guess. So
yes, I think the question has multiple layers as well. In a short sentence, we're trading economy of scale for economy of numbers. That's really what we're doing. Now, it gives you more flexibility to create synergies, meaning, our reactors, if you need, 100 megawatts of power, you'll have multiple units together, and because of the modularity of it, some of the functions, some of the systems don't need to be duplicated. A simple example is, we need a machine to refuel a reactor, but it's only being used a month every few years. If we have multiple reactors on a single site, we still need a single machine for all those reactors. So there are a number of the system, even the control room and other, ad hoc and auxiliary system. When we have multiple smaller reactors on that side, doesn't mean we have multiple of all the system. We have multiple of the core system. And so this creates synergies. And whether or not we can guarantee the outcome, just looking at the heavy industry and other industries that are comparable, they did achieve this economy of numbers over time. So now we still have to execute and demonstrate it.
Yeah, and the regulatory burden that comes from having more systems, just straight up more systems as you get larger, you're able to avoid that. And I would say that the scale up of nuclear to the current paradigm of very large reactors, that happened before there was nuclear quality assurance standards, before there was heavy regulation stemming from 3 Mile Island and other events. And they didn't pivot to what is the right scale, given new regulations. And so by you guys being able to decrease the number of active systems in order to maintain safety, it really decreases the burden on not just the capital cost, but on the regulatory side.
But also, you start to get the return after you complete the first one, right?
Right.
Only 1/10 of the investment, you start getting the return.
Yeah, it's not,
as opposed to waiting for 14 years to complete.
It is a very, very good point, because if you look at all the recent nuclear project, in Europe included, they were very, very big construction. And when something goes wrong in the construction, it's, years of delay, because you have to redo all of that. So it's also the cost of the risk, really. That's a bit more difficult to quantify. But, it is possible that as we build those units, one of them, the construction, something's going to happen. Now, it does mean that we are going to have 1 out of 10 units maybe that's going to get delayed, not all 10 at once. And there's also a lot more we could discuss about, the effective use of the labor. It's skilled labor and workforce that is required for construction of those facilities. And having multiple units in quick succession really helps with developing that aptitude and efficiency.
Actually, Florent, it's slightly still on topic of what Florent was just saying, but this came up very recently, that there was a big concern about the future of jobs just with AI's involvement in the job market. But like in the energy sector, the quality of all of our lives and the way the country is structured is going to be very energy dependent. That's going to be a really big growth area, no matter what happens with technology. So like all of those people, it's not just engineers, it's technicians, it's chemical engineers, it's everybody involved in that project. Like this is, if you don't know where the job market's heading, like this is a place to head towards, because it's going to be necessary. AI can't take your jobs unless it has power. So
And so how are you seeing universities play a role in advancing nuclear, maybe beyond just the workforce development?
Well, I won't name names, but we're anticipating building a reactor at a university, and there's various reasons for that. But one really nice thing about it is that it gives a chance for us to actually work with students directly on the reactor system, and they become very familiar with our tech. And then through that, actually, it gives us a pipeline of people that could then directly work, like move into our company, and that's going to be very important because there is going to be a squeeze, I think, on graduates. University is going to play an instrumental part of this. The future of the workforce is going to come from them. It might even be very necessary in the future to construct technical programs that are outside of degree programs, just to put the people in place necessary to be able to work all of these different systems. Because I believe in the past, at one point, our reactor system had orders for over 1,000 units. And you can imagine how much construction that would be, personnel that would be required, transportation, operation. It just goes on. You're going to need a lot of people. And like if we're not working with the universities, well, we're not going to have a business. So.
Yeah, I think it goes beyond, also just skilled, people. You have to look at the role of universities, national labs in what they've done, contributed to the nuclear industry over the last 50 years. If you look at light water reactors that were built in the 50s, they are not the same as they are built today. All the margin, everything has been squeezed by enhancement, better optimization, new technologies. We've seen, in the last decade, significant increase of the use of additive manufacturing. So I think there's a lot of development, a lot of integration of technologies outside of the nuclear, industry that can go into support of realizing what we are discussing, the cost reduction over time, new manufacturing techniques, new management techniques, and a lot of that is not going to be developed from companies like ours. We are too busy to focus on delivering on something that's complicated enough. So we are definitely looking forward to seeing universities across the US, across the world, in association with other research institutions, to push forward to demonstrate there are new technology we can make use of to make our system even better, to get more energy out of it, to increase the economics of it, to hasten the development of it. So there's a lot, really. I mean, this is a core function of universities. It's also to get those new ideas that industrial like us, and unfortunately, we don't have the luxury of time to come up with this. I think for me that's a key thing, and I encourage everybody to look at the light water reactor sustainability program that over 40 years achieved major enhancement on light water reactors.
Maybe I can add just a little bit on that, because so universities had these research reactors, and many of them still do. About 25 to 30 universities still have. But these are the reactors on which our workforce is being trained on at universities. But these were all based on the technology of the 60s and 70s and the reactors that are currently operating. For the new reactor, for the new nuclear reactors, the new technology that is being developed that we are just now talking about, I mean, for that, we need to have new type of research reactors coming to universities so that the next generation of workforce will get trained on that new technology, as opposed to, I mean, there's some commonality, of course, don't get me wrong. I mean, there's, criticality is criticality, but there are many other, facets that are different in the new nuclear. And I think the new nuclear workforce should be, we should start to train them on those new type of research reactors.
Yeah, people should know that nuclear power started at a university.
That's exactly right. Yeah.
Right. And then after nuclear power was demonstrated to be capable of peaceful use, it next went back to universities, and it expanded widely and rapidly to universities, not just across the country, but across the world. And perhaps the universities can again play a role in advancing nuclear science and engineering in that way.
Yeah, a lot of these research reactors at universities are still doing that. There's been a lot of movement on radioisotope in the last couple of decades. A lot of it was pioneered by, university and their reactors. So we also know a number of universities have decommissioned their reactors over the years. From our side, we do anticipate to see, new universities coming up with deploying advanced reactors or redeploying reactors.
Mm-hmm. So looking out 10, 20 years, where do you see nano? Where do you see the nuclear industry?
So the well,
Retired.
retired. I hope so. I mean,
10 years, not, or maybe 20.
Let's say
Yeah.
20. Like, I mean, let's be pragmatic. I think the 2030s is going to see the mass rollout of reactor systems, advanced reactor systems. So you're going to see nuclear in places you've never seen it before. I think the tech industry, we've touched on that already, but you're going to see it on military bases. You're going to see it on island communities, remote habitation. Certainly some of the projects we're looking up in Canada at the moment, there's a lot of northern communities up there that subsist off remote diesel, and they don't have any other option but remote diesel. It's very expensive. It's very polluting. You could see the integration of nuclear into maritime vessels. I think that's going to happen as well within the next, certainly next couple decades. We've even been looking at reactor systems for space, long-term space colonization. If you're actually going to try and sustain a base, like a lunar base, that almost pushes you directly into nuclear. You don't really have many other options other than that. So there's the pragmatic. You'll see the mass rollout of reactor systems, industry supporting population centers. Then beyond that, we get into more interesting areas. Ultimately leading us hopefully to space exploration and things like that. But the nice thing is that like this technology we know works. It's just got to be tamed and deployed sensibly. It's going to be commercially viable. It looks very much like it'll be like the way, especially as I think the projected costs of power is likely to increase within the next 5 years, and that's going to tie in very nicely with when the mass rollout of reactor systems comes online, because it'll just be more competitive, and that'll facilitate the mass deployment of the reactors. But it should be a very interesting time. Like, it's not going to go away. Like this, as you mentioned earlier on, it's a multi-decade thing. And so 20 years, maybe that looks very similar to 30 years. But like it's coming. Like I would say early 2030s is really when you're going to see a big sea change in nuclear.
Yeah, I mean, nuclear is, definitely set to become a commodity at this point. We see, again, looking back at the history of nuclear, was developed by, initially, universities, but quickly by the national labs. And, over the last 15 years, give or take, we've seen that there's been a lot more adoption of new technologies by startups. Before, a startup, it was institutional, entities that were really pushing it forward. You had, the 3 or 4 usual suspects, and this was basically it. And so we've been a change really moving from utilities where nobody knows where the electricity comes from the outlet, to really having visibility on what the source of energy. Even personally at home, 10 years ago, I had a bunch of people coming knocking at my door, say, hey, you can change, provider so that you have this mix of energy that will deliver to you. So I think it's a lot more openness about the system, because the application is not just for large grid application. It's more like private entities who are looking at adopting nuclear solutions. And this is why there's going to be a lot more openness and transparency on the different technology, what they can do, the right use case, and there will be widespread adoption of the solutions. At different rate, depending on the industry, of course, there's price sensitivity for everybody, but that's definitely going to be that. But so, everybody needs to understand, we're talking nuclear reactors. There's no nuclear reactor with all the supply chain behind it. So, the nuclear reactor are expensive because of all the equipment that needs to go into it, but you need people to make that equipment. So there's also the risk of bottlenecking on even simple equipment. The vessel is a big one, but there is instrumentation and control, there is substation, there are turbines to turn the heat into electricity. So there's a huge, I mean, this is the sum of it. It's a huge market. It's a huge industrial undertaking to really scale up our capabilities to deploy all the energy production we need.
Any thoughts, Rizwan? Next 10 years?
It all depends upon how much we can reduce the cost of from first of a kind to the nth of a kind.
Yeah.
I mean, if that can be done, if the nuclear technologists, the new companies that are working on it, they'll be able to, in my opinion, I think, be somewhat easily able to deliver the first one. Not so easily, but I mean, if they're not able to reduce the cost from first of a kind to the end by, I don't know, whatever factor you can think of, what factor do you expect? Is it 10, 5,
Half,
2,
half.
Well, it depends. If you look at just the mathematics of learning rate for the EV industry, historically the data for similar project, not in the energy space, have been 16%. So every time you're doubling the number of unit built, you see a 16% drop. So in our case, we are targeting 10 to 12% conservatively. Obviously, not everything goes into it. Nuclear fuel, currently the cost of mining uranium and the cost of enrichment, which is tied up to the cost of electricity. So some of that is not going to really go down. So this is why it's really dependent on the implementation effectiveness. And it's very different to say we're building, 2 reactors a year versus we're building 2 reactors over 10 years. Realizing the saving over 2 reactors a year is much easier than realizing the saving over, 1 reactor now and 1 reactor in 10 years. So this is also why smaller reactors come with the need of needing more of them, but then it increases the odds of achieving this cost reduction. Yeah. And I can give you, I can't share the price directly, but some of the equipment provider, they design the equipment, they invest their time and resources as well. They need to recover their investment, so they upcharge the first time they sell you something, and they say, oh, if you order a second one, then it is 30% off. So we have a number of quotes from providers that are like that. First time we sell you this piece of equipment, we market it up by 30-40%. Second one, we kind of sell it to you with just less markup. Beyond that, we don't have data.
So one other question that I have, I think we have maybe a couple of minutes. Between deregulated market and regulated market, the current nuclear power plants that are operating, they have very different kind of outlook based on whether they are in one kind of market or the other. The advanced reactors that we are now talking about, how sensitive they are to whether they can be deployed in the regulated versus deregulated market.
I mean, that's an advantage to it as well. Like a big civil nuclear power plant, they're going to be powering the grid. They're going to be powering civilian population centers. If you're competing with gas or coal, you're going to struggle a little bit more. Well, currently, I think the projected price is still going to go up, but still, it's always going to be very competitive. If you're competing with remote diesel in northern communities, Alaska, military bases, wherever it is, you can outcompete those quite, I wouldn't say easily, but you have big margins available to you of error, the way you could still deploy the reactor and competently beat down the cost of that remote diesel, because it is very expensive. And you eliminate obviously all the logistics costs around that and all the infrastructure necessary to keep delivering that on a daily or weekly basis. Obviously, as you get closer towards civilization, then you need to be looking at other considerations, like the number of reactors you deploy and achieving economies of scale through the utilization of shared infrastructure. But certainly, there are areas where almost off the bat, we can deploy these reactor systems to and beat out the costs of whatever they're paying for power.
Yeah. I think the question is a very interesting one. You need to look at how the electricity market price nuclear, and it needs to be priced as base load power. Now, what we're providing with the new solution, it doesn't have to be base load power. So we can do all kind of load throwing and adjustment. We can store energy because of the way we're implementing the solution. So I think there's also a need to put back into question how we consider nuclear energy. So obviously the off-the-grid market are different, but even for mainland USA, there's something to be discussed and said about how nuclear energy is being perceived, especially with smaller units. It is a lot more nimble overall than it used to be before.
Well, thank you so much for this engaging conversation. It's so exciting to think that nuclear may have a new day with a new approach that can really impact new areas. And really be a sensible solution for both cleanliness and reliability in our energy needs as we expand forward. Rizwan, James, Florent, thank you so much for being here today from the Grainger College of Engineering at the University of Illinois. I'm Caleb Brooks. Thank you for all of you who tuned in. And if you have any more interest in this topic, please reach out. We'd love to engage with you. Thank you.
Thanks, Caleb.
Thank you very much. Thank you very much, everyone.